All right, y'all go ahead and do the factoring and the math knowledge question for today. Pause the video, and then once everyone is finished, we will go over the answer. So these two both have an x squared in common. And so you factor out an x squared, and you have x to the fourth minus 4 left, which will factor as x squared minus 2 times x squared plus 2. Neither one of those will factor further with integers, so we'll leave it just like that. Looking at the math knowledge question, it asks how many whole 4-plant packs of tomatoes can she make if she takes all of the 1-plant packs and puts them together. So we've got 31 plant packs. If we take them and we split them into 4 packs, and we only want whole 4 packs, we would have 7. And we would have 2 single plants left over. So that would be your answer for both of those. So we're looking at lesson 70 today. We're dealing with properties of limits, and then we're going to look at some special limits. So hopefully after this lesson, you will be able to understand properties of limits and then some of the special limits that we're going to look at. So the limit of the sum of two functions equals the sum of the limits of the individual functions. The limit of the sum of two functions is just the limit of the individual functions. So if I have the limit as x goes to some c value of f plus g of x, I can just figure out what the limit of f is, figure out the limit of g, and then add that value and that value together. Okay? The limit of the difference of two functions equals the difference of the limits of the two individual functions. And so that is basically the same as for the sum, it's just you were subtracting them instead of adding them. So you would just do whatever the limit of the first function is, whatever the limit of the second one is, and then subtract those two values. The limit of the product of two functions equals the product of the limits of the individual functions. So you'll have two functions. F and g. And whatever the limit of this function is, you multiply it by the limit of that function. You'll just get the two values separately and then multiply them together. The limit of the product of a constant and a function equals the product of the constant and the limit of the function. So if we have the limit of k f of x, you're going to figure out what the limit of f of x is, and whatever that is, let's say it's an L, you would just say k times L to get your limit for your question. You would just take the limit of the function and then multiply the number after you get that value. If the limit of the denominator does not equal 0, then you can do the limit of the quotient of the two functions is going to be the quotient of the individual limits. So the reason it says the denominator can't be 0, you can't divide by 0. So as long as that's not a 0, you just take the limit of each individual function and then you would just divide them like they were in your problem. Looking here, if the value of a function g is greater than or equal to the value of a second function f and less than or equal to the value of a third function h, and if f of x and h of x both approach the same limit L as x approaches c, then that means that g of x also approaches L as x approaches c. I know that sounds like a lot of words. You saw several different phrases a couple of times, but it's called the pinching theorem, the squeeze theorem, or the sandwich theorem. And I'm going to draw a little picture to show you what it kind of looks like. So if g is greater than f, so I'm going to have a graph here, and we're going to put g up here. So if g is greater than f, and we'll put f here, but it is less than h. So g is less than h. I'm going to put it here. And there is a reason that I'm making them all touch right there. So this is h of x. So g is greater than f, but less than h. That would be what it said for that first part. And then it says f and h both approach the same limit at this value here. So f and h both have the same limit at this point here. Then that means that since g is in between the two functions, it is also going to approach the same limit L that h and f approached. That's why it's called the pinching theorem, or the squeeze theorem, or the sandwich theorem, because our little blue function and our green function are squeezed in that red function together until they're all the same thing at that black dot. And so that's what that property is talking about. Looking at this one, if the limit of a function g goes to L, and if the limit of a function f is f of L, then that means that we can say f of g of x is just f of the limit of g equals f of L. So it may look a little bit strange at first, but it's pretty simple to apply. It basically just allows us to evaluate the limit of composite functions under certain conditions. So it's just talking about a composite function. You would just find the value of the limit of the inside function, and then once you find that, plug it in to your f to get your actual f of whatever value you were looking for. Alright, so let's look at an example. We have the limit as x approaches 2 of f of x equals 3, and the limit as x approaches 2 of g of x equals 9. We want to find the limit as x approaches 2 of 2fx plus pi g of x. Well, since these are all as x approaches 2, we can basically just say, well, our f of x, when that limit is happening, is a 3. So we have 2 times 3. And our g of x, as x approaches 2, is 9. So we can plug in a 9 for g of x. And we end up with 6 plus 9 pi. And that would be your answer. You're basically just substituting it in since all of them are approaching the same value. Okay, looking at the next example. If the limit as x approaches a of our function equals L, can we say that f of a exists? They really like to ask this type of question on the AP exam. And it's going to have to think about all of the conceptual concepts to be able to answer it correctly. So just because the limit exists does not mean that the function at that a value actually exists. So just because they tell us that the limit exists, that does not imply that f of a exists. So can we say that f of a exists? No, we cannot. So that would be a no. We cannot say that f of a exists just because the limit exists. Because the left and the right hand limits are approaching each other, but at that value we have a hole. Well, that means that we don't actually have f of a right here. The limit does exist, but we don't have a value for our function because we've got a hole. Okay, looking at the next one. Is the following statement true? Why or why not? If the limit as x approaches 3 of f of x equals L, then f of 3 also equals L. Well, this is very similar to the last one. It's false. Is the following statement true? No, it is not. Just because the limit exists and equals a specific value does not mean that the function at that 3 actually equals any value at all. It does not have to work. So again, we could have a graph where we have a hole and then we have a dot down here. And so at this 3 value, our function is going to actually equal that, but the limit is going to equal whatever this side and this side is approaching. And so obviously these 2 values here and here are not the same thing. So that's why it is not true. Looking at this one. F is a function such that it's between negative x squared and x squared for all values of x. And we want to know what is the limit of f of x. Well, I'm going to do a little picture for you. Negative x squared is a parabola opening down, and x squared is a parabola opening up. And f is in between here. So it looks, we don't know what it does. It goes somewhere in between those two. It could just be a straight line. They didn't really tell us about it. But it asks, what is the limit over here at 0? Well, what is the limit of this function at 0? It goes to 0. What is the limit of this function? It also goes to 0. So since both of these have a limit equaling 0, that means that the limit of our f of x also has to equal 0, because it's squeezed in between negative x squared and x squared. They got pinched, and so it equals 0, just like the other two. Okay, looking here, we want to evaluate the limit as x approaches pi over 4 of the ln of tangent of pi over 4. And so that was that last property, number 7. We've got a composition here. So basically what you're going to do, you're going to take the limit as x approaches pi over 4, and you're just going to plug in pi over 4 here. Well, what is tangent of pi over 4? Well, that equals a 1. So we just have ln of 1, and the ln of 1 is 0. And so that would be the value for that limit, just equals 0. Okay, looking at some special limits, the limit of a function is a number unless it's going to be positive or negative infinity. Okay, so it's going to be some number unless it's positive or negative infinity. Looking here, what is the limit at 0? Well, on the left, we're going down to negative infinity. On the right, we're going up to positive infinity. Those left and right-hand limits do not match. They equal two different things. So this function's limit as x approaches 0 is undefined because the left and the right-hand limits do not match up. Looking at this one, the limit as x approaches 0 would be infinity because they're both going up to positive infinity. So the limit as x approaches approaches 0, this one is going to equal infinity. Looking here, well, as we approach 0 from the left and from the right, both of those are approaching negative infinity. So the limit for this function as x approaches 0 is going to be negative infinity. Y'all remember going over those earlier in the year? Okay, so this is an example of a limit that does not exist. The left-hand limit is approaching negative 1, because that's what our y value is here. The right-hand limit is approaching a 1. That's our y value there. Since those two values do not match up, as x approaches 0, the limit does not exist. Okay? This one also does not exist. You can graph this on your calculator, and you can zoom in and zoom in and zoom in, and it just keeps going back and forth, up and down from negative 1 to 1. It's actually a kind of cool graph to look at if you want to look at it. You just need to make sure you put your graph in radians or your calculator in radians whenever you go to graph it. But it's a pretty cool little graph if you zoom in really, really close. So these are two where the limits do not exist. This is one that you just want to memorize that the limit does not exist. You may not be able to use your calculator on the AP exam to just plug it in and look at it. So you need to know that the sign of 1 over x, as x approaches 0, it does not exist. Okay, so on your homework, you get to omit number 14, 15, and 16. So make sure that you do your homework so that tomorrow we can go over any questions that you have.